Okay, so welcome everyone to the first session of the third day of the conference. So this is a session about obfuscation, and I'm your session chair. So I must say I'm not really an expert on obfuscation, although I'm interested in the topic. So I hope we'll have many questions from the room so that I don't have to embarrass myself with stupid questions. So I count on you. And so our first talk will be given by Marc Gendry. It will be about the relationship between evasive obfuscation and quantum money. So let's go on.
Thank you. Okay, so the topic of this talk is going to really be about quantum money and the barriers to building it, but the focus of this particular work will be on trying to construct quantum money from obfuscation. Okay, so to motivate quantum money, consider the following problem, which I call the double spend problem. So here we have an adversary and they have a banknote, and they're going to try to spend it give the banknote to two different people, which of course would be bad in a money system if the adversary could do this. So to prevent double spend, in the classical world, basically we always need some coordination between Alice and Bob. Possibly this involves a third party like a bank, or in the case of cryptocurrencies it would be the blockchain, but there needs to be some communication between Alice and Bob and possibly some third party. So things change, however, when we enter the quantum world. And the reason is that we have this thing called the no-cloning theorem that says that if you have a quantum state, you cannot, in general, copy it. And this led Wisner, about 50 years ago, to propose what is now called secret key quantum money. And basically, you take the no-cloning theorem, and you just set your banknote to be a quantum state. And the no-cloning theorem says that now you can't clone these banknotes. So the result is that we have actually now solved the double spend problem. The limitation, though, is that we actually still need coordination in order for this to work. And this is because in Wisner's scheme, in order to actually verify the banknote, you need to go to the mint and actually ask the mint, is this a valid banknote or not? And if you don't do this, then the adversary can just put in their own quantum state and you would have no idea. This limitation led Scott Aaronson to propose the notion of public key quantum money. And in public key quantum money, the mint produces a banknote and then gives it to someone, and they can just verify it locally for themselves. They can then send it to someone else and who can verify it, and you can just keep sending it and everyone can verify it for themselves. But if an adversary ever tries to spend it twice, they will be caught. He is not able to take the same banknote and send it to two people and have them verify. So public key quantum money really does solve the original problem that we set out to solve, where you can actually solve this double spend problem without any coordination between Alice and Bob, because they just do all the verification locally. All right. And more generally than the application to money, public key quantum money is just a central object in the study of quantum protocols. It's kind of a necessary starting point to solve many other things, such as copy protection for software and others. All right. Okay, so we've had this notion of public key quantum money for over 15 years now, but it has been notoriously hard to construct. There have been a number of proposals in the literature, but it turns out that many of them have been broken. And really the difficulty is that a lot of these constructions were largely ad hoc, based on new computational assumptions, and then those new computational assumptions turn out to be false. So what we really want is a construction of public key quantum money based on tools that have been widely studied by the cryptography community. And we do have one construction of this flavor. This was something we showed a few years ago based on ideas in prior work. We know how to construct public key quantum money from what is called indistinguishability obfuscation. And to date, this remains the only scheme with provable security under assumptions studied by the wider cryptography community. Okay, but on the other hand, indistinguishability obfuscation is this really heavy hammer. The the quantum security of obfuscation is still not fully settled. And so we really want to base these quantum money schemes off of milder assumptions than full-fledged indistinguishability obfuscation. So the question we ask in this work is, can you build quantum money from a weaker object called evasive obfuscation, which is obfuscation for programs where basically it's hard to find an accepting input to the program. Why do we care about evasive obfuscation? Well, it turns out that certain classes of evasive obfuscation, we actually know how to realize securely with provable security under LWE, which is a typical post-quantum cryptography assumption. And also just in the classical world, there have been a number of results showing how to base security of applications that originally required I/O, or indistinguishability obfuscation, from milder tools such as LWE. And oftentimes these results go through the route, maybe implicitly, of basing security first on evasive obfuscation and then instantiating the evasive obfuscation. So if we could base public key quantum money off of evasive obfuscation, this would be a pretty good step toward actually getting a construction relative to standard cryptography assumptions. And the second observation is that the prior work actually almost seems to use evasive obfuscation. So the idea in the prior work is that what you're going to obfuscate are random subspace is a random subspace S and its orthogonal subspace S perp. So on their own, except for this kind of uninteresting point at the origin, obfuscating a random linear subspace actually is evasive. You can't find an accepting input other than the trivial origin to a random subspace. And so if you had evasive obfuscation for subspaces, this, intuitively it seems like it should work. However, I kind of lied. And the reason is that while the obfuscations on their own are evasive, you're not given just the obfuscation. You're actually given this banknote as well, right? The adversary actually sees the banknote in the system. And the banknote actually is this quantum state that is a superposition over S, or you can massage it into a superposition over S perp. And what this does is it actually allows the adversary to find a non-trivial vector in one of these two subspaces. So technically, the prior construction cannot use evasive obfuscation, but it seems very, very close. So in this work, we're actually trying to see if we could base the construction off of evasive obfuscation, since it seems like we're almost there. Nothing we tried worked. So we thought about it a little more and eventually arrived at this following result, showing that more or less we can't construct public key quantum money from evasive obfuscation. So the main theorem is that public key quantum money cannot be based in a black box way on evasive obfuscation under some assumptions about how the quantum money scheme works. So what are the assumptions that we make about the quantum money scheme? So first, we assume that the mint only makes classical obfuscation queries. It's not trying to obfuscate a superposition of programs. And this is a really natural, did the audio? Oh. This is a really natural restriction in the context of obfuscation because that's how we would normally use obfuscation, even in a quantum world, even all the applications of obfuscation for quantum protocols, they generally only have the individuals obfuscate classical programs as opposed to superpositions over programs. The other restriction we make that's probably a bit more fishy is that we assume that the verifier makes no obfuscation queries. So the verifier is only allowed to make evaluation queries, potentially on superpositions. So they can evaluate superpositions of inputs, but they can't make obfuscation queries themselves. Right? So under these two structural assumptions on how the money scheme works, we show that there's no black box construction of quantum money from any form of evasive obfuscation. All right, and as a corollary to this, We note that evasive obfuscation in particular captures, like a one-way function is a sort of evasive obfuscation. And so as a corollary, we actually show that you can't, in a black box way, construct public key quantum money from one-way functions. Now, one-way functions are naturally considered much weaker than evasive obfuscation, but even such a separation has not been known before. However, there are some major caveats to this result as well. Basically, the mint can only make classical queries to the one-way function, and the verifier has to have some natural restrictions. And these restrictions correspond to the 2 bullet points in our main theorem. And I'll note that this corollary is actually a rough dual to a somewhat recent work that showed that you can't construct public key quantum money from one-way functions where the verifier's queries are classical. So they showed that the verifier's queries can't be classical. We show that the mint's queries can't be classical. So maybe this is some progress to kind of a full separation between quantum money and one-way functions. All right, so now I'll just give a very high-level overview of our ideas. So for black box separations, we follow the typical approach of defining an oracle, and our goal is to have this oracle, relative to this oracle, evasive obfuscation will exist, but public key quantum money will not. All right, so what does our oracle do? It's basically an oracle that provides obfuscation for you, except we have to be a little careful because the natural way of providing an oracle that gives you obfuscation actually would give you public key quantum money. So what does our oracle do? We have an oracle O that maps circuits to bit strings that's going to represent the actual obfuscator. And then we have a second oracle that's an evaluation oracle that just allows, you take this obfuscated obfuscation of a circuit C, an input X, and it'll just tell you whether C of X is 0 or 1. So that would capture obfuscation, but as I said, relative to this oracle, we can actually instantiate the subspace scheme and get secure quantum money. So we have to break things somehow. And so the way we break things is if you have an accepting input, so if C of X equals 1, the evaluation actually spits out, it doesn't just tell you that the evaluation was 1, it actually spits out the whole code of the circuit C. So if you ever find an accepting input, this completely breaks the obfuscation. All right, but nevertheless, if you don't find an accepting input, then this is basically as good as full-fledged obfuscation, and this allows us to show relative to this oracle any meaningful notion of evasive obfuscation is actually secure. Okay, so we have evasive obfuscation, and now what we want to show is that you can't have public key quantum money. How do we do this? Well, okay, so we imagine this mint. It only makes classical queries to the oracle per our restriction. And then the mint provides this quantum money state to the verifier, and then the verifier can make verification queries, but no obfuscation queries. And as I said before, we're going to allow superposition queries. And one more structural assumption that we'll make that we can actually make without loss of generality is that the evaluation queries were only ever on programs produced by that were actually obfuscated by the mint. So that's another assumption we need to make, but we can actually obtain that without loss of generality. All right, so how are we going to try to break this supposed quantum money scheme? Well, the observation is that if the adversary is actually able to obtain all of the CI, all of the circuits that were obfuscated by the mint, then the scheme is broken relative to computationally unbounded adversaries. So we will allow unbounded computation by the verifier, but still restrict their queries. And even in this model, evasive obfuscation exists. And if we can show that public key quantum money does not exist, then we're happy. All right, so what's our attack? Basically what we're going to do is we're going to take a banknote and we're going to run the verifier, because it's a public operation, we can do this. And we're just, every time the verifier makes a query to the evaluation oracle, we're going to measure the result. And the result is either going to be bought if it was a rejecting input, or it's going to be one of the programs obfuscated by the mint. Okay, so if there's just a single program obfuscated by the mint, we're actually in really good shape. So we'll break into two cases. First, suppose that measuring the query actually gives this program that was obfuscated by the mint with some non-negligible probability. Well, then the scheme is broken, because with non-negligible probability, we'll actually recover the obfuscated program, or the program that was obfuscated by the mint, and once we've recovered that, we've recovered all of the mint secrets, and we can break the scheme. Okay, on the other hand, suppose that measuring the query actually gives bot with overwhelming probability, but this means that we didn't even need to make the evaluation query. If we always knew that the evaluation query was going to return bot, we don't have to make the evaluation query at all, and this means that the evaluation oracle is actually useless, and we can remove it. And if we can remove it, then information theoretically, the scheme is broken. It's not hard to show that public key quantum money does not exist. Information theoretically without an oracle. All right, so now let's consider the full scheme where maybe there's many obfuscated programs by the mint. So what we're going to do is we're just going to keep running this. We're going to run the verifier, measure a query, run the verifier again, measure a query, and so forth. And the hope is that by doing this, we'll eventually pick up all of the programs obfuscated by the mint. Or if we don't, then we can argue that the evaluation oracle is useless. And this is the approach we follow, but there are some technical caveats to getting this to work. And the issue is that in quantum mechanics, we have this thing called the measurement principle, which says that measuring a quantum state actually changes it. So when I measure the query by the verification algorithm, I might no longer have a valid banknote. I might have actually broken the banknote, and this ruins all guarantees for future evaluations. And we show that we can actually fix this by relying on some techniques developed in prior works, where we show that you can basically repair the banknote every single time and get back a valid banknote. It might not be the banknote you started with, but we show that you can always recover some valid banknote, and then by a careful analysis, we can get everything to work. All right, so the main open question that we leave behind is, can you actually separate public key quantum money from either evasive obfuscation or from one-way functions without any restrictions on the protocol design? And I should mention that we really inherently, in our techniques, really do need the restrictions that we have. And the prior work actually also really inherently needs the restrictions they have. So it seems like really some brand new ideas are going to be needed to achieve this open question. And with that, I will conclude my talk. Thank you.
So we have time for questions.
Sorry. One quick question. So could you compare your restriction on the verifier not calling the obfuscation to, there's some CCA separations but called shielding reductions, like where you can't call the encryption algorithm.
Right.
But then in real life you kind of use that a lot, or maybe it's a little further.
Yeah, I mean, certainly it's a restriction. Now, I guess the contrast to the CCA setting is that, to the best of my knowledge, in the context of using obfuscation for quantum protocols, we don't have any examples where you actually have the mint or related entities.
Oh, you don't have a positive example.
Yeah, we don't have any positive examples like that. But yeah, that if you could interpret the negative result as just guidelines for actually ultimately developing quantum money from these tools, and the guidelines would say that you do need to, if you wanted a scheme from evasive obfuscation, you would have to go this route of actually having the mint make quantum queries to the obfuscation, or have the verifier make obfuscation queries.
Any other questions? If not, we're right on time. So,
all right, thank you.
Go on to the next talk. So the next talk is going to be about quasi-linear I/O, and it's going to be given by Yaohua Ma and his co-authors.
Thanks. I would like to begin. Today, I would like to talk about our paper, quasi-linear indistinguishability of obfuscation via mathematical proofs of equivalence and applications. This work is joined with Chen Xindai and Yilin Shi. Okay, let's begin. First, I would like to talk about something familiar, that is indistinguishability of obfuscation. Given two functionally equivalent circuits C1 and C2, an indistinguishability of obfuscator I/O can generate a pair of computationally indistinguishable circuits IOC1 and IOC2, where they preserve the functionalities. During the last decade, I/O has become the most innovative and significant primitive in the modern crypto, since it has numerous applications, including functional encryption, two-round MPC, SNARK, and so on. Clearly, the most foundational problem related to I/O is the feasibility. In 2013, GARC-ACL gives the first candidate construction from some multilinear problem. Since then, the community has made many attempts to improve their construction, culminating in the recent breakthrough JLS 2022, which constructs I/O from 4 well-founded assumptions. By contrast, relatively few efforts has been made to improve the concrete efficiency of I/O. Indeed, owner I/O constructions suffers from some polynomial overhead, which makes the theoretical results far away from practice. We may wonder that, why can't we have an efficient I/O construction? Zhang and Jun's paper partially responds to this question. They conjecture that there exists some folklore barrier towards efficient I/O called the impedance barrier. Specifically, they claim that the security reduction for I/O must check the functional equivalence for two programs. Thus, the number of hybrids is exponential in the impedance. As a result, each hybrid can only tolerate exponentially small security loss, and the security parameter should be made as large as a polynomial in the impedance. Fortunately, Zhang and Jun also observed that for almost all known existing I/O applications, the programs need to be obfuscated often have a succinct propositional logic proof of equivalence, where the length of proof is roughly the circuit size itself. A propositional logic proof is a type of mathematical proof with only zeros order logic. From this observation, they proposed a new relaxed I/O security definition, where only concerned about the programs with succinct propositional logic proof of equivalence. For such definition, they present a generic method to circumvent the impedance barrier. For more details, Zhang and Jun's construction only relies on the fact that a succinct propositional logic proof exists, but doesn't suppose it to be even computable. If such a proof exists, then their method can circumvent the exponential security loss in the hybrid argument. However, their construction still suffers from polynomial overhead, now coming solely from the obfuscation and evaluation algorithm. Thus, we may seek to ask, under the same assumption of Zhang and Jun's paper, can we expect a more efficient I/O, or can we construct a cosilinear I/O? In this work, surprisingly, we give a formative answer to the both questions. Assuming the hardness of learning with error, Y functions, and I/O for small circuits, we succeed to make cosilinear I/O, specifically for circuit families of size at most n-city and proof length of at most n proof. Our obfuscated program size and the evaluation time are both bounded by O lambda n circuit plus n proof. The next topic is the technical overview. Obfuscating a large circuit with a complicated functionality is indeed a hard work. In order to achieve efficient I/O, we may try to divide the gates into individual ones and obfuscate them one by one. The advantage of this approach is a natural cosilinear complexity, no matter what the internal obfuscation algorithm we use. However, this approach also leads to new issue. Now, the adversary can obtain the whole structure of the obfuscated circuit. Hence, in order to prevent the intermediate result leaking, we have to encrypt both the inputs and outputs of each gate. Here, we illustrate a simple 3-gate circuit. You can see that both the outputs of gate 1 and gate 2 are encrypted by a secret key shared with the third gate. After this process, the adversary cannot easily gain the intermediate result, and the security can be protected. We then define the notion of O-log equivalent circuits. Two functionally and topologically equivalent circuits are considered as O-log equivalent if they only differ by a small subcircuit of O-log size. Here, topologically equivalence means that if we ignore the functionality of each individual gate and only concern about the connections between the wires, we can obtain two identical circuits. For example, here C1 and C2 are O-log equivalent except the color blocks. Since the gates outside the blocks are all identical, the functionality of the two blocks are also equivalent, although they might have slightly different codes. From this concept, we will consider a weaker version of I/O called locally indistinguishability obfuscator, where we only require the outputs to be indistinguishable when obfuscate two O-log equivalent circuits. To instantiate LIO, we will adopt a gate-by-gate approach. Now it is time to describe Zhang and Jun's blueprint. First, they show that given a proof of equivalence, we can pad the circuits into a form that can be transformed via a polynomial length sequence of O-log equivalent circuits. For example, here the circuits C and C star share a short proof, then they can be padded and transformed via the sequence C1, C2, and so on, where each adjacent circuit pairs are all identical except an O-organized subcircuit. Then they propose an algorithm to pad a circuit into fixed topology, depending only on n circuit and n proof. Third, they construct a LIO. Finally, by a simple hybrid argument with respect to the aforementioned polynomial length sequence of O-log equivalent circuits, we can prove that the LIO of paddy circuit is just a generic obfuscator. However, Zhang and Jun's construction still cannot achieve a satisfactory efficiency, as we emphasized before. This is partially due to their inefficient padding algorithm, which requires quadratic time. Another reason is that in order to prevent a mix and match attack, they have to hard all the directly and indirectly dependent wires of each gate G. To do so, they used a primitive called somewhere extractable hash and require unpadded bugs, each for up to unpadded circuits. This incurs another quadratic complexity. To resolve the efficiency issues, we propose a new cosilinear padding algorithm, also an efficient SEH construction for a more restrictive purpose. We observe that we don't actually rely on a generic bug, but only proving the consistency for some prefixes of a sequence is sufficient. Thus, we can use an incremental algorithm to significantly accelerate our SEH construction and achieve a cosilinear complexity. Here, we compare Zhang and Jun's result and ours. You can see that even with the best known bug construction, Zhang and Jun's approach still requires at least n to the 4 plus epsilon complexity, whereas ours is just cosilinear. Then we'll talk about how to achieve the promised improvement. The first challenge is to shrink the petty circuit size. We first use a subroutine called pad_single, which takes a circuit C of size n as input and convert it into fixed topology depending only on n. With the help of a routing network and a hierarchical data structure, we can instantiate pad_single in n log square n time. We won't go into the details. There. The petty circuit can be decomposed into 3 parts representing the 2 original circuits and the proof. Each of them is built with the pad_single subroutine. Initially, the last 2 subcircuits are just placeholders and constantly port 1, and the output is said to be the end of proof part and C1. Apparently, this value is just the output of C1. We claim this construction is correct. To see this, we only need to show how to transform from the petty version of a circuit C1 into another functionally equivalent circuit C2. First, we will switch a placeholder subcircuit to represent C2. The output is unchanged since it is independent of this subcircuit. Then we can switch the proof part to hardware an equivalence proof between C1 and C2. At a high level, the proof part will still constantly output 1, since a mathematical proof only comprises of tautologies. Then we can switch the output from C1 to C2 with the help of equivalence proof. Finally, after an almost symmetric argument, we can switch back C1 and the proof part and obtain a petty circuit of C2. Moreover, we can prove that the change during the pad algorithm can be shown as a polynomial length O log n equivalent circuit sequence. Another challenge is efficient SEH construction. We will illustrate a typical obfuscated gate via the gate-by-gate obfuscation approach. Both the input wires are encrypted, and the gates will receive them as input. It will first verify a max sigma 1 and sigma 2. If the ciphertext passes this test, then it will simply decrypt them and compute the result. Finally, it will output also an encrypted value. However, a malicious adversary can launch a mix and match attack to fool the obfuscated gate by mixing the ciphertext from 2 distinct evaluations. That is, here the ciphertext 1 and ciphertext 2 may correspond to 2 distinct input settings in different evaluations. Drain-drains patch is to use an additional consistency check. The obfuscated gate will also receive 2 hashes H1 and H2 corresponding to the ciphertext and H prime corresponding to itself. The gate will also verify the max and the consistency proof high corresponding to the hashes. However, this leads to efficiency issue, since the hash contains the information of all its dependent wires, and the proof high should be as long as all its directly and indirectly dependent wires, which can be as large as the circuit size itself. For example, here we consider this 3-gate circuit. Notice that the wires W2 and W4 are independent of them. In drain-drains approach, we need to prove that the gate 1 and gate 3 are consistent with the wires W1 and W3, similar for gate 2. Our inference is that although the wires W2 and W4 are independent of this subcircuit, we will still know their values when iterating these 3 gates. Thus, we can let the hash also contains the information of the wiped part. Then, the dependency of gate 1 and gate 2 will simply become a prefix of dependency of gate 3. Thus, we only need to prove the consistency between some prefixes. Our SDH construction is based on Hubeck and Wich's work in a non-backwards way. The SDH construction combines the idea from FHE and Merkle tree. Notice that in a Merkle tree, we only use O-log nodes to represent a prefix those. Proving the prefix consistency for two prefixed HX and HY, we only need to compare the information on all the nodes with the stars, O-log numbers. By an incremental algorithm, we can compute all n hashes and proofs in a quasi-linear time. Our paper also gives two applications of our circuit work, a quasi-linear multi-input functional encryption and a quasi-linear I/O for Turing machines. Finally, we leave some open questions related to our work. First, we are interested in improving or disproving the input length barrier. Second, although we only require a polynomial secure I/O, we still use some sub-exponential secure assumptions. Those eliminating the use of sub-exponential security assumptions will be also an intriguing work. Finally, I think instantiating our work will be a significant step towards concretely efficient I/O.
Any questions? So I guess to start, I have a kind of a naive question. So do we have in usual usage of I/O, do you have examples of two circuits for which we have a short polynomial proof of equivalence?
Okay.
Propositional.
Thank you for your question. As we shown before, almost all I/O applications can have a propositional logic proof. For example, a typical framework, the puncture argument, that is, we use a puncture PIF in the I/O body can be shown by an EF proof, which the length of the proof is only if we use a GGM-based puncture PIF, then the length of proof is roughly the depth of the tree. It is significantly shorter than the domain size, which can be exponential in the depth.
Okay, any other questions? If not, let's thank the speaker again. So the final talk of the session is going to be about multi-authority registered ABE, and George Liu is going to give the talk.
Yeah, hello everyone, I'm George, and this is a joint work with Brent Waters and David Wu. So, yeah, I'll be talking about a multi-authority registered attribute-based encryption, and so there's a lot of adjectives in this title, and so we can start by just talking about the notion of like attribute-based encryption. So this is some like generalization of public key encryption where there's a master public key, but there's also potentially many individual secret keys. And these secret keys are going to be associated with attributes, and the functionality you sort of want in an attribute-based encryption scheme is that any encryptor can come along, look at the master public key, and use it to define a ciphertext associated with a policy over this attribute space. And now for a particular user who holds a secret key, if they happen to have an attribute set associated with their secret key that satisfies this policy, then they should be able to decrypt the ciphertext. But importantly, any secret key holders who don't satisfy the policy, even if maybe they say like jointly satisfy the policy, shouldn't be able to collude and break the security of this ciphertext. So attribute-based encryption has been this very large topic of area of study, and there's been tons of work in the past, I guess like 2 decades now, both building and sort of looking at applications of attribute-based encryption. But maybe one kind of limitation of this definition is that there's this huge focus on this like central authority. So in like this attribute-based encryption scheme, as you saw in the picture earlier, in order to make this work, we have to have this central authority, which is sort of in charge of creating this master public key as well as issuing all these user secret keys. But what this means is that when you kind of want to use the system, you have to place a huge amount of like trust and responsibility on this user. And since they're in charge of issuing secret keys for users, they also have a master secret key which can decrypt any ciphertext generated from this encryption system. And so if they happen to misbehave in some corrupted way, or even if they somehow like accidentally had their master secret stolen, then this would entirely compromise the security of the ABE scheme. So sort of in the direction of trying to mitigate or remove these, such like a central point of failure, there's been like a couple different lines of work on sort of defining variants of ABE that are in a way like less centralized. So one of these is this line of work on multi-authority ABE, which as the name might imply, rather than having a single authority which is in charge of this producing this one master public key, instead different attributes can sort of be associated with different authorities who can independently generate their own public keys. And now when an encryptor wants to define their access policy over, say, some subset of these policies, they just have to look at the appropriate master public keys and use that to produce a ciphertext. In a sort of separate direction, another line of work on registration-based encryption and registered attribute-based encryption has been focuses instead on this issue of rather than having a central authority with a persistent master secret key, instead replacing this with a less trusted key curator. And so the goal of the key curator is to essentially have this central authority that does not have a master secret. And so how this is accomplished is instead users themselves will generate their own individual public keys and secret keys and send their public keys along with their attribute set to be registered to this key curator. And so just going a little more in detail into these definitions, in this multi-authority attribute ABE scheme, the key point here is that we want these authorities to act essentially as a regular ABE authority and be able to issue secret keys sort of associated with the attributes that they're in charge of. But crucially, they shouldn't need to coordinate at all, and we should still achieve the same sort of functionality as a regular ABE scheme, where here, say, this first user should be able to take these two key components he got from these independent authorities and use them to decrypt the ciphertext. In addition, we also want to capture the same collusion resistance notion from the original notion of ABE, where these other users, even if their attributes, say, jointly satisfy the ciphertext, shouldn't be able to decrypt a ciphertext which their policy doesn't satisfy. So if you just look at this picture as is, you might wonder, well, this doesn't seem quite possible, right, if the authorities aren't able to coordinate, because how would they know if these green keys and red keys are belonging to different users or not? So in order to kind of get this definition we want, we kind of relax the model a little bit, and we work and multi-authority ABE is generally defined with respect to this global identifier model, where every user is associated with some unique, but not necessarily cryptographic identifier. And sorry, I thought I removed that, but anyways, and so going a bit more into registered ABE, so here the goal is to have the functionality for an encryptor exactly the same as a regular ABE scheme, but instead, what the key curator's job is to sort of take these public keys from individual users and use them to incrementally produce this master public key that can be updated as users come in. And so, sort of to capture the efficiency of a regular ABE scheme, we require that this master public key is short and doesn't grow with the number of users that come in to be registered. And to sort of capture this notion that this key curator is like some untrusted party, we require that essentially their operations are entirely deterministic and transparent. Now, again, kind of like the multi-authority setting, this picture sort of as is isn't quite realizable. So to give the key curator a little bit more power than maybe in the regular ABE setting, we do allow them to send some infrequent decryption updates to the back to the public decryption updates back to the user, and typically this is realized with a honestly generated common reference string. So perhaps the question of this work is, can we have both of these properties in a single encryption scheme? So the first thing that we do is we define this notion of multi-authority registered attribute-based encryption. So if you're looking at the last two slides, this definition perhaps is probably exactly what you expect. On the right-hand side, you kind of have the functionality of a multi-authority ABE scheme with these independent key curators. But on the left-hand side, you're working essentially in this registration model, right? Where users are where users are sending over their public keys and attributes to be registered with the appropriate key curators. And so now that we've defined this is great. But of course, maybe this is only interesting if we can actually build it. So for the, I guess like next half of this talk, I guess I'll try and give like a high-level overview of the techniques we use to maybe the techniques that prior works use sort of to get multi-authority and registered ABE sort of separately, and then maybe some technical challenges that we have to overcome to kind of get these things to work together. So just for a bit of background, these, just like ABE, both multi-authority and registered ABE have been built from like a variety of crypto assumptions, notably like pairing groups, lattices, and some forms of obfuscation. For the purposes of this talk, we'll be focusing on just the pairing group setting. Right. So yeah. So let's start with the just multi-authority ABE. So at a high level, like if you have ABE from groups, how these pairing-based multi-authority ABE schemes are built is that these ABE schemes seem to decompose nicely into these couple group elements associated with each attribute. So what authorities can really do is just generate sort of part of what looks like a regular attribute-based encryption scheme, and then when an encryptor wants to come along, they can kind of like take a look at like the sort of just the concatenation of everyone's of all these authorities master public keys. If you squint and look at it, it kind of looks like an ABE master public key, and you can use that to sort of encrypt a ciphertext and policy. And so, but sort of where the challenge in realizing multi-authority ABE is getting these independent key components to work together from independent authorities. And how this is kind of generally done is that, remember, we have users are associated with the global ID. So this global ID, individual authorities end up querying a random oracle on this global ID to derive some like shared common random group element, which is then used to derive these key components and tie them together in a way that allows them to decrypt a ciphertext. Now, moving on to registered ABE, at a high level, what happens in a registered ABE scheme is that you have several copies of this, you have several copies of the ABE, sort of an ABE scheme in the ciphertext. And when users come along, what they do is they can kind of look at one of these schemes and sort of derive an ABE public key from one of these schemes in the ciphertext. And as different users come along and they sort of occupy these slots in the ciphertext, what all the key curator has to do, since this is where we're living in this like group-based scheme, is that these master public keys are just some series of group elements. So all that the key curator does is just multiply them together and compress it into something that looks like a short ABE master public key. So this is great for encrypting. It is essentially an ABE master public key, but sort of to support correctness, what you additionally need, of course, is that you can actually use this to decrypt. And so we're not quite done yet, right? Because even though this master public key has contributions from each of the individual users, if these individual users sort of try and directly decrypt this as if it were their own ciphertext, they would end up with some term dependent on the message, which comes from their own key. But they also end up with all these other contributions that sort of arise when other users master ABE public keys were multiplied in. So to sort of maintain correctness, what we also need to include is a bunch of these cross terms, which are essentially just these additional helper group elements, which help you remove these contributions from one user when some other user is trying to decrypt. So if you look at these two schemes, right, you can be like, well, it seems like these are like fairly generic. Why is it not immediate that you can get a multi-authority registered ABE? So maybe one of the first challenges, if you try writing this down, is you can see that if you kind of if you write down the actual ABE scheme, what you'll notice is that what sort of corresponds to the random oracle output in this multi-authority setting in the regular ABE scheme is the same thing as these like slots in the CRS. And so there's like hello? Oh, okay. There's a bit of a conflict here, right? Because for the correctness of our registered ABE, we need this to be some like very structured, and to give out these like structured additional terms based off these group elements, but we can't exactly do that with a random oracle output. So it turns out in our setting, we can actually replace this with just some algebraic hashing and use that to sort of preserve and give out sort of the relative cross terms relative to this hash function. This does complicate maybe the security argument later on, but unfortunately, I will probably not have time to get to that. And so I guess another issue sort of along the same theme is sort of trying to get this structured, this sort of structure of this registered ABE scheme to work with the lack of coordination in a multi-authority ABE scheme. And so if you recall, in the registered ABE scheme, these users have these unique slots that they have to occupy within that they register to. But if you have multiple different authorities, these different authorities, users can come to different authorities in different orders, and there's not necessarily the same, if they don't end up registering to the same slot, then you can no longer guarantee sort of correctness of your underlying ABE scheme. And so the way we kind of fix that is that we sort of slightly expand the number of slots in our scheme, and we instead ask users to register to some subset of slots based off some combinatorial, based off as a function of their global ID, based off these combinatorially cover-free sets. And using these, we can guarantee that users are able to have a unique slot which they are registered to among all authorities. Sorry, I think I was supposed to remove these slides because I will not have time for them. But sort of so there are some additional complications sort of arising from some of these changes we made in arguing security of our proof, and we do have to introduce some new techniques here, but I guess the end result is we're able to construct pairing-based multi-authority registered ABE for bilinear groups, supporting bounded users and monotone pooling formulas, essentially what you'd expect from the combination of registered ABE and multi-authority ABE from groups. The slight caveat is that we do have long decryption keys, but interestingly enough, unlike the plain multi-authority setting, we don't require a random oracle. In addition, we do construct an obfuscation-based multi-authority registered ABE scheme, essentially with optimal parameters. Yes, thank you. That's my talk.
Are there any questions?
Hi, thank you for the great talk. So I have one quick question regarding the motivation of combining them together.
Okay.
So you first say that in the multi-authority ABE, I want to remove the single point of failure. So in some sense, if I have multi-authority and sort of one authority is malicious, then maybe we still have some security left, right?
Yeah.
I guess that's what we want. And then in registered-based ABE, the key curator is always honest, right? There's no secret for the key curator. So in some sense, there's no point of failure there. Then why do you want multi-key curator? What's the motivation of?
I mean, I think in a practical setting, I think it's kind of important that you both have the people who sort of you want to sort of I think the point of the multi-authority thing is you want to distribute authority to the sort of the management of these attributes to maybe the appropriate authorities, like in our example, right? In sort of the example on the slides, if the attribute is something related to your university, you want maybe your university to be managing that. And sort of as you have more authorities, even though these authorities can't sort of break the entire system, you still don't really want to trust them, right?
I see.
If you can help for it.
In some sense, for multi-authority, what you get is not just spreading what you get is not just security guarantee. You also get some good functionality in the sense that it
yes.
partial. Okay, I see.
Yeah.
Any other questions? If not, let's thank the speaker again and all the speakers of this session.